So if we have a parametric, or I'm sorry, if we have a vector value function, perhaps we want to find the equation of a tangent line. And so that's what we're going to do. It shouldn't be too difficult. So what we're going to do is we're going to first find the derivative, just like we did in Calculus 1, to find the equation of the tangent line. And then we're going to use that as the rate of change, or the slopes, at each of those points. So we're basically going to find the value of t. That's going to give us the slope at each of those, and then we can find the parametric equations at that point. All right, so the first thing we have is we have this polynomial sort of vector function. We have ti, t squared j, 4/3 k, and we have the point 1, 1, 4/3. So the question is, what is the value of t? All right, and it's actually pretty easy for this one. So t equals what? And what you can do is just say that, just look at the first coordinates and just set the coefficient equal to the first coordinate inside of there. Now this one's really easy. T equals 1, right? Now what you would want to do is you'd want to check just to make sure. And if it doesn't work, then obviously the problem's not going to be a valid problem, because that means that the point's not necessarily on the curve. All right? So if we substitute 1 back in for t squared, that gives us 1 squared, which is 1. And then it doesn't matter what we plug in for 4/3, it's always going to be 4/3. All right, so that's what I would do. I would just set one of probably the first of the components equal to the first coordinate of your point and solve for t that way. All right, so let's find r prime of t, okay, to be able to get a tangent line. And r prime of t is going to be 1i plus 2tj. R prime at 1 is going to be equal to I plus 2j. Right? And technically 0k. And remember, we have our formula for our parametric curves. So remember, x equals x naught plus at, y equals y naught plus bt, and then z equals z naught plus ct. A, b, and c are going to be the coefficients of the derivative. So in this case, a equals 1, b equals 2, c equals 0. And I just got those right from the coefficients. And then x naught, y naught, z naught are going to be the point. So x naught equals 1, y naught equals 1, z naught equals 4/3. And we're just going to substitute directly back into the parametric equations. So x is going to be equal to 1 plus 1t. Y is going to be equal to 1 plus 2t. And then z is going to be equal to 4/3 plus 0t. Right? So that's our parametric equations, and we do have to define the value of t. T is just a real number. Right? So that's not too bad. We just go through just like we did in Calc 1, find the derivative, get the slope at that point, and then substitute that back in, except now we have these parametric types of equations. A second example, 2 sine ti, 2 cos tj, 4 sine squared tk. So what we want to do is first define the value of t. So we're going to start by saying 2 sine of t is equal to 1, or sine of t equals a half. Right? And then we just have to go into our unit circle and remember, where is the y value equal to a half at what angle? All right, and it's realistically either going to be pi 6, pi 4ths, or pi 3rds. All right, and just by doing a little bit of memorization of the unit circle, we're going to say that pi 6 is going to be equal to t. And of course, we want to verify that. All right, and if we go back through and plug it into the other two coefficients, then it does give us respectively root 3 and 1. All right, so that's our value of t at that point. Now we need to find r prime of t. All right? Now the first two are pretty easy. So that's going to be 2 cos of t I minus 2 sine of t j. Right? And then what about this guy right here, this 4 sine squared of t? All right? Now, off to the side, couldn't we rewrite that as 4 sine of t square, which means that it's a chain rule problem. Right? So what we would do is we'd multiply 4 times 2 to get 8. We would keep the sine of t, but then we'd also have to multiply by the derivative of that interior function, which is cos t. Right? That's going to be our k. Right? So make sure that you're okay doing those derivatives. Right? Now the next thing that we're going to do is we're going to substitute pi 6 back into r prime of t to be able to find our slopes. So that's going to be 2 cos pi 6 of I minus 2 sine pi 6 of j plus 8 sine pi 6 cos pi 6 of k. Right? And just a little bit of trigonometry. We probably remember that the cosine of pi 6 is root 3 over 2. The sine of pi 6 is a half. Right? So that's going to be 2 times root 3 over 2 is going to be root 3i. Sine of pi 6 is a half, so that's going to be minus j. And then 8 times a half is 4. 4 times root 3 over 2 is going to end up being 2 roots of 3k. And at this point, now we're set to be able to find the parametric equations. All right, so our a, our b, and our c are given by the derivative at pi 6. The point we had, I believe, was 1 root 3, 1. Right? And so x is going to be equal to 1 plus root 3t. Y is going to be equal to root 3 minus 1t. And then z is going to be equal to 1 plus 2 roots of 3t. Right? And again, t is a real number. Right. So hopefully this illustrates how to find the equation of a tangent line at a specific point on a vector value function. So the last topics that we're going to be taking a look at with respect to these tangent vectors is the principal unit vector. And that's going to be a little bit tougher with respect to the mechanics. So we'll get there in a few moments.